Hi everyone. So now we are going to continue to talk about the solid space today. So last time we introduced the multidimensional solid space. So first let's review the definition. So let's say that you have a domain, omega is in Rn. It's a general domain, okay? So we're going to build a solid space on this domain. So here, so this is the solid space. It's called WKP. So it's high order solid space. So the order is K. So this is equals to, so all the functions in the LP space, omega, and also exist the weak derivative. So weak derivative we denote by d alpha and f. And all these weak derivative has to be in the LP. So this is in LP omega. Okay? So as long as this multi-index, so last time we talked about multi-index, the order of the multi-index less or equal than k. So this is the solid space WKP over the domain omega. Okay? So we're going to see example later. Well, this is a very simple definition. And d alpha, so alpha, so maybe a little bit more about alpha. Now what is d alpha? D alpha is basically the partial derivative. So this equals to, let's say alpha is equals to, so alpha 1, alpha 2, up to alpha n. So this n dimensional space. So this multi-index must contains n components. And the order, the norm of the alpha, which is the summation, alpha 1 plus alpha 2 plus up to alpha n has to be less or equal than k, because this the maximum order of derivative is k. Okay, so this d alpha f is basically the is basically a partial derivative. So d alpha, okay, the f, and then the dx1, the Hamming order, alpha 1's order. Then dx2, alpha 2's order, up to dxn and alpha n's order. So that's the partial derivative. So this is a shortened noting, very easy notation for the partial derivative, okay, called d alpha. Okay, so this is the solid space. Now what is the, what I mean by the norm of this space? So the norm of this space and the f and kp, basically, so this equals summations, and j from 0 to, no, so this, you cannot use this, because we are summation, making summation over the alpha. So you have to do it this way, with alpha is less or equal than k. Okay, then you have the d alpha f and the p's power, the LP's norm. So this is the norm, the solid space norm. And so when k, so the summation is over alpha less than k, right? So it's also included when alpha equals 0. Alpha equals 0, so this means that you have to just talk about the function itself, not the derivative. Okay, so here we have the arrangement, so maybe you can call it d0, then alpha equals 0. And this is just arranged to be the function itself. Okay, so this norm. So that under this norm, so this become a normed space, because we know that for LP space, you can have the Minkowski inequality. So using that Minkowski inequality, you can show that this norm is actually satisfied the triangle inequality. So it's a normed space. And later, we're going to show that this space is a Banach space, meaning that under this norm, it is complete. Okay. Now first, let's see an example first, okay, before we prove the completeness. A simple example for you to demonstrate exactly what is the components in this space. So let's say that you're talking about this case, W2, think about this case. So let's say that the K, N equals to, so the omega is actually contained in R2. So dimension is 2, okay? It's not a one-dimensional case. And let's talk about the W, the second order, okay? Second order, and a piece power, okay? So let's consider this. So what is the space? So this is basically the F in the LP omega, as usual. Now here, we're talking, in this example, we want to be very specific about the alpha things, okay? So this means all the pocket derivative. So if we write it up, in this case, in n-dimensional case, you can see this portion, the weak things. So what we want to have is the, it means that they exist. They exist, weak pocket derivative. Okay, the weak pocket derivatives mean that first order and second order, because this is the second case too. So this is a df dx1, so that's one of the first order pocket derivative, and then you did another one, dx2 should also be included. So you have to include all the pocket derivative, including the mixed type. So then you go to second order, so that's df dx1 squared, then d squared f dx2 squared. Then you have a mixed derivative, d squared f dx1 and dx2. And normally that's enough because the other mixed derivative is the same as that. Okay, it's basically all you can include it, and d squared f dx2 dx1. You put all these things together. So if the space is a subspace LP, so that these pocket derivatives, these all weak pocket derivatives, they all belongs to the LP. Okay, and then this will be the space W2P. Okay, now if you have a more complicated, higher dimension, or you will have the higher order, so basically, in this portion will get more complicated. But however, if I use the d alpha notations, use multi-indexings, so it's very easy to written up the entire space, entire definition. All right? So that's the more examples, okay. And also we mentioned about this is the standard norm. Okay, you can also define the other equivalent norm. Okay, so we don't have to say. I assume you all understand that. Okay, we actually talked about this last time. And also another thing is that when p equal to 2, okay, so when p equal to 2, and this will become, it's not just the normal space, it's the space with the inner product. Okay, so how do you see that? So you p equal to 2, then you can define f and g. And k, okay? The case order. So this is going to equals to the integrations over omega, and you have alpha less or equal than k, then you d alpha f times d alpha g. G. Okay, you just multiply. So this is one of the pocket derivative. You multiply another pocket derivative with the same multi-index, and then you summation, make a summation over all possible multi-index, which is less than k, and this will become the inner product. Okay, and this inner product actually is going to give you the norm, the corresponding norm. So this will imply the norm. So f the K2 norm when P equals 2. So this norm is just equals to the inner product F and F, the case, they take 1/2. They take 1/2, that's the norm. So once we prove the completeness, you can see that in the K equals 2P case, this space is not going to be just the Banach space, it is also the Hilbert space. Okay. All right, so now we are in the position to talk about the completeness. Actually, in the one-dimensional case, we have already proved the completeness. Basically, in the multi-dimensional case, we're repeating the same argument, except the notation is a little bit more complicated. Right? So let's see. Let's give a proof of completeness. All right, so let's prove. Okay. So this is the proof about the completeness of WKP. Okay. And how to prove? So in order to prove the completeness, we are supposed to show that every Cauchy sequence has a convergence sequence, right? Is a convergence sequence. So let's choose that the FM, FL. So we're not making mistake again, not to use K. Okay, so this in WKP, okay? WKP. And so this is going to be sometimes one thing I forgot to say. Now when you use this space, notation of this space, WKP, okay, sometimes we write this more specific, KP and omega. So this indicates that this is a solid space over the omega. Okay, so just like this, okay, omega. So this is a Cauchy. It's a Cauchy sequence. Okay. Now what we are Cauchy sequence? So this means that the norm FL minus FM KP. So this norm is going to 0 as both K and L goes to infinity. More specific. KP, okay. So this means the L, no. This FM. So this norm KP, so this summation goes to 0 as K and L goes to infinity, right? So again, making mistake. So Lm goes to infinity. So this is what I mean by this sequence is Cauchy in WKP. Okay, now you can look at the norm. So the whole summation goes to 0. So this simply means that if you look at individual term, if you look at this individual term, it's also goes to 0 if L and M goes to infinity, right? Okay, so obviously this is true. Okay, so this indicates that if you focusing on each individual term, so you can see that this each individual sequence, the weak derivative sequence FL. Okay, and this is also Cauchy. So this is so this sequence is considered is LP. Okay, is Cauchy. Now these two Cauchy are different. So when I say the first one, this sequence is Cauchy. Okay, when I say this is Cauchy, so this means this is Cauchy under this norm. Okay, and when I say this is Cauchy, this one Cauchy, we're thinking about this is a sequence in LP. So this is Cauchy in the LP norm. It's a Cauchy in the LP norm. Okay, so different. Now since for each alpha this is a Cauchy sequence, in the LP node. So this means that our LP space is a complete space, right? So therefore, this will imply that the D alpha F L, so this is a weak derivative sequence, is going to be converge to something in the LP. Okay, it's going to converge something in the LP set, converge something. So I'm going to write this thing is F alpha, simply a notation indicating that this one is a limit of this weak derivative sequence. Okay, alpha corresponds to this multi-index. Okay. All right. So let's look at the relationship about the weak derivative. So I know that the D offset by this relation. So if you integrate the F to the D alpha, the testing function, and this one is equals to, so there's a minus sign involved. So equals to what? Equal minus 1 alpha. Okay, then integration omega, then D alpha F. Now this time, and this is first we apply this to the sequence, okay? So FL and D alpha L. Then times the B. So they must be equal. Okay, so if you concentrate each member in this weak derivative sequence, is set by this. And this relation simply say that D alpha L is the weak derivative of FL. And this derivative exists because of the assumption. Okay, now you can see that the FL. So, so because you can see that the D alpha FL goes to that, including what? Including alpha equals 0. So this means that the FL will also convert into something, right? So this is equals to F0. So D0 F1. So basically, it's converted to something, but I would like to denote this just by F. Okay? So therefore, you can see that if I take the L, letting L goes to infinity. Now in this relationship, so then you can see that this relationship will give us that. So I'm going to write this on the top. Okay. So this relationship now, if letting L goes to infinity here, and then you can see that this will give us the integration F D alpha phi equals to minus 1 alpha integrations and D, not D, because D alpha L. So this sequence goes to this, it's equal to F alpha and B, like this. So we get this. Easily we get this, okay? And from this, then we have to, from here, you have to understand what does it mean. So this simply means that by the weak derivative definition, so this means that the D alpha is the weak derivative. Now what is weak derivative? That's a D alpha F for F. It simply means this. So this means that our limit function, now this limit function here, F, carries the weak derivative D alpha L. D alpha L, okay? So therefore, so this is true for every alpha less or equal than K. So this means that the F is in the WKP. Okay? It's not just saying that this belongs to WKP, but it's also saying that our whole sequence, the F L is converged to the F in the WKP. Okay. So this simply says that this Cauchy sequence actually has a limit in WKP. So this means the completeness. So this completeness. This is proof complete. Now this proof is very standard. It's very classical. So it's applied to the general case. So this is something you need to remember, okay? But maybe in the final, I will give you some problems and with some specific n and specific k, and you should supposed to reproduce this result by yourself. It's not difficult, but I really want you to understand the proof of this, the argument behind this. Okay, so this is one of the things I can show you that the and so this is the so therefore this space is a finite space because it is a complete space. It's a complete space. Okay. All right. So let's continue. So I'm going to say something else about this before I give example. I don't know whether today it will be have enough time to give a more specific examples. Okay. So what I'm going to say is that now when you work on this space, okay, you can see every function is the LP function basically. Now when we deal with LP function, sometimes it's inconvenience, right? The LP function is just the measurable function, and the derivative is just another measurable function. So when you deal with measurable function is carries some kind of uncertainty principle, uncertainty property. For instance, if you change values, the function is not going to change. So sometimes it's not easy to handle if you compare with the function in the classical sense, okay? And then you can see that this function is very difficult to handle in the general setting unless you use the reanalysis technique. But sometimes we actually like to use like the classical technique, okay? Like you can apply trying to use some classical theory as a tool to handle this space, okay? But you can't do this directly. So here, actually we have a way to get around of this. It's because that in some sense, even though this is a rough space, but however, there's a very nice dense set. Okay, there's a very nice dense set you can work with. Just like the LP function. LP function is separable space, right? And we know that the certain kind of the characteristic function can be the dense set. Here in the solid space, we can even find a better dense set because it carries the weak derivative. Okay. Now here I'm going to tell you a surprising result and without proof, because in this class I'm unable to give you this detailed proof. Okay. So this result is like this. It's called approximation theory. Okay. So we can say that. So this it's an important theory. So what does it mean here? Now WKP, you cannot imagine what kind of function inside, right? But however, you will be able to consider this. You consider this. The C infinity function. Now what do you mean by C infinity function? Okay, so omega. C infinity function means what? So this is just the function carries any order of the partial derivative, right? It's a very nice function, very smooth function. So this is some kind of function and we would like to work with. Now, however, and you don't know whether all these functions is inside WKP or not. Actually, it's not, because it all depends on whether the function is integral or not, right? So you can have a very nice smooth function, however, this function is not in LP, not even in LP. So for those functions, it's useless. So what we really want is the intersection of WKP. So we think about all the C infinity functions inside the space. Okay, C infinity function. And then we look at, so this is maybe a very small set, but however, this is a very nice set because, so this function will be in LP space, it has to be LP, the weak derivative is going to be LP. Okay, now it's because this is intersection, so this function at the same time is infinite. So all these weak derivatives is actually become the strong derivative, right? So you can see this is a subset of WKP, but will be a very nice set. Now, what is the relationship between this set with WKP? So there's a surprising result. It's going to show that actually this set is dense in WKP. So what does it mean is if I put a bar, you put a bar here. Now, when I put in bar, it means that you're talking about the closure, right? Now, when you talk about closure, what do you mean by closure? It means that you take a closure under the norm of WKP. So sometimes people write there, under the norm of WKP, okay? Because if you use different norm, you get a different closure. Okay, so this result saying that actually this one, if you take the closure, then this is exactly equal to WKP space. So what it means is that suppose you have so the consequence, important consequence is that suppose you take a function f in WKP. Okay, suppose. Okay, this function carries many derivative and whatever, all the weak derivative only, and the function itself may not be that smooth. But however, based on this result, so they exist. Okay, the sequence FL, and this space is actually in significant. Okay, significant, but of course it is also in the WKP. Okay. So basically saying that you can find an infinite function such that the FL will converge to F in the WKP sense, in the WKP node. Now this is a big deal because you can see that if you deal with directly the function F, now it can be very complicated because you don't know, the function may not be smooth function, right? But however, it's very easy for you to handle the FL. Your FL is a significant function. You can take the derivative in the classical sense, differentiate and do whatever you want, okay? But the good thing is that this kind of nice function can be used to approximate f in this norm. And in analysis, sometimes this is give us a very useful tool. So that means, well, later I'm going to show you example how to use these tools. It's basically saying that now you have to handle the WKP function. And you only need to first work on the significant function, okay? You only need to work on the significant function and getting the result you want. And once you get this result, you take the limit, and because you can use approximation argument, and then the result for the significant case, okay? And through this approximation can extend it to the result of f. So that's the trick. Okay, so in the solid space, and later when we prove some inequalities and relationships, and I always begin to work the significant function first. Okay, and then we use approximation argument extended to the WKP function. That's a standard argument. Okay. All right, so I'm able to show you this a result like this later. So I'm going to show this result later. Okay. All right. So now when we talk about the omega space or omega domain is a general domain. I didn't put any assumption, any restriction, right? Now suppose we can in this direction we can actually get a better result. Okay. Now suppose. So this is another theorem without proof, okay, without proof. So suppose the boundary. Now what I mean by boundary of omega? Okay, so this means, let's say this is omega. So the boundary is basically a lower dimensional hypersurface, right? Now in the two-dimensional case, you can see this boundary is just curved. Okay, what we mean by, so this is the boundary. So what we assume here is the boundary is smooth. Okay, now what we mean by smooth, so this curve is not going to carry any corner or discontinuity. Okay, so at this level, I can't tell you what exactly the definition of smoothness on the boundary. So basically, like curve case, the curve actually can be look at locally to see the smoothness to see the specific smoothness of this curve, right? Now, in a high dimensional case, so the boundary is a hypersurface, and if you localize the surface, and this surface in some modern language, it can be considered as the manifold. Okay, so if you use a local coordinates to see this manifold, and you can define what kind of smoothness is required here. Okay, but anyway, so assuming this boundary is smooth, sufficiently smooth, and then I have a better result. So here when we talk about the single-infinity case, I'm not talking about the boundary behavior of this single-infinity function, right? Now here, suppose the boundary is smooth, then I can just use this class. So that's the single-infinity function up to the boundary. So any function like this, it means that it's not only smooth inside the omega, and it's smooth up to the boundary. So it can go right to the boundary. Okay, on the boundary, for instance, you can talk about restriction of this function on the boundary, and then the restriction itself will become another smooth function on a low dimensional manifold. Okay, so this is a better function like that. So this function actually is a subset of single-infinity omega. So in this case, actually you can get this, and you take bar in this sense, and again over this norm. Okay, then this is also equal to WKP. Okay, so this is a better result. So in this case, with a smooth boundary, this means that you can actually and you can use single-infinity omega bar function to approximate the general function in this surface space. Okay, so this is another important result. Okay, right, and so let's see. So this is so we have talked about how to approximate this. So we are unable to give a proof on this, right? So at this moment, at this point, I don't know whether you still have any question, because I want to make sure that it's not going to be going too fast in this class, especially for the surface space. Okay, so first I want you to understand these things. Now here I'm going to give you the final example. The final example is about the relationship with the partial derivatives, the weak derivative we talked about last time. Actually, I left the homework problem, like the homework problem is suppose you think about one dimensional case, okay, and W KP and AB return to the one dimensional case, but however the argument also works for the multi-dimensional case, okay, and suppose the L plus H, so this is a positive integer, is less or equal than K. So this is a case order solid space, right? So the weak derivative exists until the case order. So here, remember what we were trying to do last time? If the F, L's derivative, so what we talk about derivative, then we talk about weak derivative, right? And the H, then you apply the H derivative, H order derivative, you take another derivative, H order, and this is exactly equals to, so both derivatives are taking the weak sense, okay? This is also equal to F, L plus H, the weak derivative. So that's the things I'll ask you to prove in the homework, okay? And so I'll just trying to give you example, like suppose you talk about W 5P AB, okay? And let's say that you want to prove that F, the third order derivative, so there's a triple derivative for this function, then you take another second order derivative, then this equals to F5. The fifth order derivative, okay? And that's the relationship, right? Okay, so this is actually something I want you to prove. So actually I'll take this as an example and give you argument for that, okay? So, so first you take the f3. Now what we mean by the f3 here? F triple derivative. So this means following. This means f integration AB, and you have f3. Now f, then the phi3, right? So this is going to be and equals to, so this is minus 1 to the 3's power. So I put it symbolically. So this 3's power. So that's basically equals to minus 1. All right. But because I want you to remember the relationship between here, the order and the coefficient here. So equal to AB. Okay. Then equals to f triple derivative, weak sense, and times the phi. So this is the result we get. Okay. And and then you can see about these things, about the fifth derivative, and I have another result. The definition AB, then F, then F5, so this should equals to minus 1, 5, then AB, then F5 to the phi. So that's a definition for the fifth derivative, like this. So here we are trying to combine these things together to create this, to create these things. Okay, so the idea is that you look at the first things here, okay? And you can see that this is true for every phi function, right? Every testing function. So what you do is replace this phi, okay, by the second derivative of phi. Well, first, when you replace, so if phi is a testing function, then the second derivative is still a testing function. Okay, so you can allow to use the phi second derivative as the testing function. Now, why do I use phi2? Because that 2, because of this 2. Okay, the same 2 here. Now, if I replace this, so this equation becomes the following. AB, F remain the same. Then you get phi23. Phi23 is basically what? Because phi is a standard, is a classical function, so this is just a phi5. No difference, okay? And then this equals to, still, it's minus 1, minus 1 what? Minus 1 3. It's nothing is changed, okay? Nothing is changed. And then you can see this is the integration is a to the b. And then again, you can see that we are going to, so this F3 sitting here. Then you can phi what? phi2. Yeah. All right. So I just simply replace the phi by phi2, and you get this new identity. Then the next thing is I'm going to compare with this. Now, if you compare with this, obviously you can see this term equal to this term, right? So therefore, these two terms are equal to each other. These two are equal now. Okay, but however, they are equal because, of course, they have a different sign involved here. Different sign here. So you can cancel the minus 3 with the minus 1 to the 5th. And then you can get the following. So if you combine these two, you can see that you're going to get the, starting from here, okay, starting from this is the left hand side. It's just like a F, AB, and F, so the minus 1, 3, here, 3, and the phi2. So this equals to minus 1, 5, AB, and F5 to the phi. Now this is all we need, because why? Because from here you can simplify it. And you can simplify, you can pull this one to the other side. You multiply the minus to the cube, both sides for instance. So this will end up with F3 phi2 equals to what? Now, the minus 1, 5, then times minus 1, 3. So this is exactly equal to minus 1, 2, right? So this is actually 1, but I still leave it as symbolic notations. It's equal to F5. See? Okay, now how do you understand this one? So to understand this one, you have to treat this as a one function, right? Think about this just F. And here the phi is what? Phi is second derivative, okay? So this is supposed to be the second derivative, second weak derivative of this function. Second weak derivative of this function. So this is basically saying that from here, it's obviously it's give you F3, then take this another derivative, 2. This is exactly equal to this guy. That's F5. So this is what it means. So for the classical function, this is obvious, but what we proved is that this is also true in the weak sense. Okay, so that's an example showing you how to handle this relationship with the derivative. Now, when this is understood, then you can just prove the general case without any problems, right? So I think this is today's lecture. I'm going to stop here, right?